In the second part of section 6.1, we're looking at using and solving proportions and how they apply to geometry. We used proportions last year in algebra again, but we're looking at some geometric aspects and using them in real life. Keep in mind a proportion is an equation. Equation has an equal sign that states that two ratios are equal. Now a ratio can be written as a fraction. So in this case I have one fraction, a over b, equals another fraction, c over d. And why did I do these two different colors? In geometry we kind of have some terms that we're going to use, and we're going to talk about geometric mean later in this section. The two blue spots that I wrote, b and c, are called your means. Notice they're diagonal from each other, and actually the two red spots are called your extremes. Not ultra important, but something that you should just be familiar with and have heard once or twice. The means are diagonal, the extremes are diagonal. And why is it important that they're diagonal from each other is because you know that the way to solve a proportion is to do cross multiply. To solve a proportion, it's called cross products property. We know that if we have one fraction equals another, a over b equals c over d, then we pretty much cross multiply. And actually we say the product of the extremes, which would be a and d, remember those are in the extremes spots, equals the product of the means. B and c are in the two spots that are called the means, so a times d equals b times c. The product of those means equals the product, or multiplying the extremes. So today we're going to practice doing cross multiplication to solve a proportion, and we're going to look at some real life examples. Remember that when you cross multiply, the important thing to realize is when you have that fraction or that fraction bar, that vinculum, anything on the top or bottom of the fraction in the numerator or denominator, if there is a quantity, it is in parentheses. So remember those invisible parentheses and be careful and make sure you use those when you're solving proportions. This first example, very basic, finding that x. Nothing to worry about here, and you can probably do this all in one step on your calculator. But we're really doing the product of the extremes here, so doing 2 times 8, which gives me 16, is equal to the product of those means, which is x times 5, which I would write as 5x. And of course I would divide by 5 on both sides, and 16 divided by 5 would be 3.2. So first example, very simple. What about here? Make sure that if you have a quantity, remember that this x minus 3, because that's subtraction, there are invisible parentheses here. This is more than one term. There are those invisible parentheses, but you have to put them when you go to solve. When I do 4 times x minus 3, I'm doing 4 times the quantity x minus 3. This will then force me to distribute that 4 in just a moment. And that's equal to the product when I do 1 times 3x. Well, that's just 3x. To solve for the variable, I'm going to distribute on the left. 4 times x, and 4 times negative 3, so minus 12. And that equals 3x. Let's see, I got x's on both sides. I'd probably subtract the 4x and get rid of it here. So I just have negative 12 there. Now if I subtract 4x here, subtract 4x on the right, 3x minus 4x would be a negative x. And then really what I'm doing here is changing the signs because I'm dividing by negative 1, remember, is technically in front of that x. Dividing by negative 1, and x equals 12. Because my negative 12 divided by negative 1 will turn to positive 12. Looks like that's fine in the denominators, and we're all good there. Alright, one more example where again I have to be careful. There is a quantity, there are invisible parentheses here around this y minus 3. So when I do 14 times that y minus 3, I better put it in parentheses. It is a quantity. And that would equal my other cross product, 7 times y. Distribute on the left. I get 14y minus 14 times 3, giving me 42. And that equals 7y. Again, this is the only number, so I'm going to keep it here, but I'm going to subtract 14y on both sides. 7y minus 14y is negative 7y. Divide by negative 7. Negative 42 divided by negative 7 would be positive 6. and we're good to go. So again, solving proportions, you cross multiply, make sure you put quantities in parentheses. Let's use proportions then to solve real life problems. For a science project, you need to estimate the total number of blue spruce trees in a 50-acre forest. You count 36 trees in 3 acres. This is actually a great example of sort of a sampling and something that happens a lot in science. We counted 36 trees in 3 acres. Notice we did a smaller section of forest, counted the trees, but we need to estimate, this was only 3 acres, we need to estimate how many are in 50 acres. But using this sample space, we can assume that the ratio is probably pretty close to the same, so I can set up a proportion here. Now I might use the one that I have both pieces of info for first. I counted 36 trees in 3 acres. These go together, so I'm putting them in the same fraction. Notice 36 is the number of trees on top, 3 is the number of acres on bottom. So when I go to set up the next fraction, I better put trees on top again, acres on bottom again. We need to estimate the total number of blue spruce trees in a 50-acre forest. I know that there's 50 acres. Acres was on bottom, so it goes on bottom again. I don't know the number of trees, I'll just call it X or T or whatever you want. And cross multiply to solve. Okay, 36 trees in 3 acres, how many trees in 50 acres? Let's see. So 3 times X is 3X, 36 times 50 is 1,800. Divide by 3, and it looks like we're getting about 600 trees. This is what we're looking at in what we would think to see in 50 acres. Okay. Again, setting a proportion, solving for what we needed. Let's try another example below. Looks like we're cooking here. You need, or baking I should say, you need 2 cups of flour to make 1 large batch of 84 cookies. How many cookies would you make using 5 cups of flour? Alright, here's what I know. I need 2 cups to make 1 large batch of 84 cookies. That goes together, right? 2 cups makes 84 cookies. How many cookies would you make using 5 cups of flour? Alrighty. I'm going to set up my first ratio. 2 cups applies to 84 cookies. And I'm just going to label up here so that I know 2 was cups and 84 was cookies. Because now I know that should be the same ratio for this next example where it was how many cookies, I don't know how many cookies, but let's see, I would make using, okay, I know I'm using 5 cups of flour. Cups was on top, so I'm putting 5 cups on top, and I don't know how many cookies, so that'll be X or C or whatever you want on bottom. 2 cups made 84 cookies, 5 cups makes how many cookies? Cross multiply to solve. 5 times 84 is 420. And that equals 2 times X. Divide by 2. It looks like we have 210, and this would be cookies, would be made from that 5 cups. Seems reasonable. If 2 cups made 84, 5 cups making 210, sounds good. So using proportions to solve for a real-life problem. Again, be aware that the same sort of label should apply to the things on top and the things on bottom. By the way, these aren't the only way you could have set up this proportion. There are a number of ways you could have set this up. I could have switched both of them. I could have done 3 over 36 and 50 over X. I could have switched both this way, like I could have done this fraction first. There's a lot of ways to switch it up as long as, key thing is that the same things are diagonal from each other. There's a lot of ways that you could even mix these up as long as the same things are diagonal from each other. The next thing we're looking at in this section is called geometric mean. Now you're familiar with the term mean, which also is the same as average. When we are finding the mean or the average of numbers, you know you add them up and divide by how many there were. So if you're finding the mean of 2 numbers, you add them up, you divide by 2. That's called arithmetic mean, though. This is geometric mean. Now, to find geometric mean of two numbers, it's the number x, so that a over x equals x over b. And notice that the geometric mean x is in those spots where the means go. Remember how these are called the means, and these are the extremes. So if we're finding the geometric mean of a and b, you put a and b diagonal from each other, whatever the two numbers are, whether it's like 5 and 30 or whatever. You put the numbers diagonal, and the geometric mean is the number that would show up here and here, so x is repeated. Now the cool thing is that you would obviously solve these all the same because you're cross-multiplying. So you always end up doing a times b, and you always end up doing x times x. And we're trying to find what x is because that's the geometric mean. X is the geometric mean. So I'm going to solve for x here. Well, x times x is x squared. And we know that should equal the product here of the extremes, a times b. I'm just going to write as a times b. And then if I was trying to figure out what x is, because that is the geometric mean, whatever you get for x, you end up taking square root to undo squared. So it turns out that the geometric mean of two numbers is the square root of their product, or what you get when you multiply them. So remember how arithmetic mean you would add, divide by 2? Geometric mean, you multiply and take the square root. So it is sort of some type of average or number in the middle. It should geometric mean will always be in the middle of the two numbers somewhere, but it's just a different type of mean here. So let's look at some examples. Let's find the geometric mean of 12 and 27. Again, because it's geometric mean, it should be somewhere in the middle of 12 and 27, so you can tell if your answer is anywhere on the right track. Setting this up, we're looking for geometric mean, and that is x. You put 12 and 27 in for a and b. So you're thinking it's 12 over x equals that same x over 27. Notice I put the numbers diagonal from each other. And again, to solve, we're going to see what I had just shown. You cross multiply, so you'll always get x times x or x squared, and you end up multiplying the two numbers together. So I'm trying to find geometric mean of 12 and 27. I multiply 12 and 27. I get 324. And then you will always end up taking square root, because if you're looking for geometric mean, and I had x squared there, I have to take the square root of both sides to figure out just x. And the geometric mean, when I take the square root of 324, it is a perfect square. Geometric mean is 18. Notice 18 is somewhere between 12 and 27. It looks like that answer works out. So geometric mean ends up multiplying the two numbers that you're finding the geometric mean of, and then taking square root. Let's try one more example here. Geometric mean of 18 and 54. Geometric mean means set up a proportion. Put the two numbers you're finding the geometric mean of diagonal from each other. And the geometric mean will be x, which will be in both mean spots. These are your extremes. Cross multiply. X times x, again, gives you x squared. 18 times 54 is 972. Undo squared by taking square root. So again, you end up multiplying the two numbers and then taking the square root of what you got when you multiplied, of their product. Here, the 972 is not a perfect square. We get a decimal. That is common. I'm going to go to two decimal places. I get 31.18. Actually, it rounds up. You can check that on your calculator. So today, solving proportions, and then looking at proportions in real life, and using geometric mean, multiplying two numbers and taking their square root.